Alright, so the idea here is section 5.2, we're talking about the definite integral. And we already talked about this in the last section. We just didn't actually spell it out. So here's the idea. We took the limit of the last section, if you recall. We took the limit as either n goes to infinity or delta x goes to 0, whichever way you like to review it, of the sum of I goes from 1 to n of the f of x sub i's times the delta x's. Okay? And we said that the limit of that is the integral. Okay? More specifically, it is the integral of f of x from a to b. Okay? So here's what we do. This is how we write this. This is the integral sign. That's what this curvy-wurvy sign is here. They say it's like script S for the sum. Okay? So you can kind of view that. From a to b, and you'll recall that our delta x over here was b minus a over n. You'll recall that. Notice that our delta x has been replaced by this dx. The idea of the dx is called the differential. In this particular setting, what it's being used for right here is kind of like an appendix, kind of one of those appendages that's there, but you don't really use it anymore, kind of a deal. But it gives you the idea of two-dimensional, because that's how you're going to get your area. And so, in reality, it forms the same basic process. The difference is over here was an actual number. Over here is more just this, what do you call that, an appendage that's not there anymore. It's there, but you don't use it. It'll come to me, okay? And so how do we do these? Well, here's how we do it. We take the antiderivative of f of x. So cap f is the antiderivative of little f, okay? And so, what do I do with it then? Well, I write it like this, from a to b. And how do I do it? Well, I take f of b minus f of a. Okay? That is how you find the definite integral. So you may recall in the very last video we did, we had something like 2x cubed plus x squared from negative 2 to 2. Okay? To take the definite integral, it's the antiderivative. And then you evaluate it from negative 2 to 2. In other words, you take 2 times 2 to the 4th over 4 plus 2 to the 3rd over 3 minus 2 times negative 2 to the 4th over 4 plus negative 2 cubed over 3. So what does that come out to be? Well, this is 16 over 4 is 4 times 2 is 8. This is 8 thirds minus, this is positive, so that should be minus 8. And then distribute the negative to here, it's going to be minus a minus 8 thirds. I swear, every time I sit down to make a video, the allergies hit me, which is 16 thirds, which is 5.333. Brother. Love spring. Don't like my allergies. Okay. Now, let's do another one. 3x to the 5th minus 2x plus 5 minus sine x from, oops, what are you doing? dx from 0 to 4. Cool. So what are you going to get? You're going to get 3x to the 6 over 6 plus, minus x squared plus 5x plus cosine from 0 to 4. Cool. Now, here's the deal. You can plug all that into your calculator, but that just seems silly to me. So what I like to do is I like to use the computer here, and I like to put in, and I like to do it like this. Oops, not a squared, you idiot. Try again. To the 6th. Divide by 6. There you go. Minus a squared plus 5a. Nope. Plus cosine. There's a reason for this. Okay? I want to evaluate this thing. Okay? So that's what I have to do. I have to evaluate it. So I'm going to evaluate it at 0. And I'm going to write 1. So remember, this whole thing right here is f of x, right? Big F of x. So I need to do f of 4 minus f of 0. Well, f of 0 I just found to be 1. So I'm going to plug 4 in with that slider. And I get 2051.34. So my answer is 2050.34. Okay? Now someone might well ask, could you check this with, using midpoints or, and doing it that way? Yeah. Could you check it using the summation situation we did? You could, if you knew what the summation of x to the 5th was, because that's what we had on the previous, in the original function. We didn't have that, but if you knew what that series was, you could totally do it that way too, and if you knew what sine was. It's a little messy, sine is. But sine turns out to be an odd polynomial too. So you could get a pretty good approximation doing it that way. It would just be kind of gross. Okay? Here's a question. Let's try this one here. 3x to the second minus 6x plus 1 dx. You will notice that when I take the antiderivative, I'm just going to end up with this minus this plus this. Notice that I did not write plus c. Some people are weirded out by that. You shouldn't be weirded out by that. Because what's going to end up happening is I'm going to then evaluate it from -7 to 2. And what's going to end up happening, I'm going to have some number plus c minus blah, 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 plus c. When you distribute it through, what's going to happen to that c is going to subtract out anyways. So we don't show it. Because it'll be the same for both of them, and it will always subtract off. So it's going to be 8 minus 12 plus 2. That's what happens when I put in the 2, correct? Minus. So that's going to be -7 cubed minus 3 times -7 squared plus -7. This looks like -2. This looks like -343. It's positive 49. It's going to be minus 147 minus 7. So if you distribute that, well, let's add it up first here. That's going to be this plus this is a 0. Carry 1's a 9. 490. 497. So it's going to be -497. So it's going to be -2 minus a minus 497 is 495. That would be your final answer. Now, interestingly enough, if a person were to graph that, see what it looks like, the original function that is, 3x squared minus 6x plus 1. And you wanted to go from negative x equals -7 to x equals 2. The question is, how much area is under the curve? Well, interestingly enough to note, there's a lot of area. You see this up here? There's a lot of area. That's a lot, Jay. Yeah, you're not a kidding, pal. There's a lot of area. See how high up it goes? It goes up here. It crosses at 190. But that's a lot of area, dude. There's a lot of positive area under this curve. Okay? And then it goes negative down in here. There's a little bit of negative area under here. You can see it, right? Right? From like 0, from about 0.184 to here, it's negative area. And then just a skosh of positive area, in between on the other side there. When you add it all up, it adds up to 495. That's a lot. And so that's kind of a neat, easy way to check yourself to see if that looks reasonable for an answer. Now, some of the interesting things about this. Remember, the integral is a limit. The integral is a limit. It's also a summation. So from either of those two things. So if you have the integral from a to b of some f of x plus g of x, what can you do? Well, you can break it into two pieces. It's the integral of from a to b of f of x plus, dx, don't forget your dx, plus the integral from a to b of g of x dx. They are the same. Likewise, if you had c times f of x dx, what could you do with that c? Well, it's a constant, so you can, that's right, pull it out. And if that makes you happy, well, you knock yourself out. Here's a question. What would happen if you integrated from a to a? Wait a minute. So you mean to tell me you've got a function doing this, and you want to know how much area is from here to here. Jay, there's no thickness, there's no area. That's exactly right, sir. Well done. Because it would end up being f of a minus f of a. It'll always be 0. Yes, this is true because of the definition, but this is a fact because there's no width to it. Hey, what would happen if you integrated backwards? If you went from b to a, what would you get? Well, the way I like to think of it is this. You know that if you have a function here, this was your f prime of t, right? Let's say t, and this is our t. So like it was velocity, and you went from time equals a to time equals b. You picked up some displacement. You went somewhere. What if you ran time backwards? What would you get? Well, you'd get the opposite, the negative, if you'd have gone this way. So in other words, that one we just did a minute ago from -7 to 2, whatever that function was. No, here, right? We'll just do it right here. I'm too lazy. That would be equal, so negative of this fella. They're opposites of each other. And if you did this one, you would end up with positive 400 and, what did I say, 490. You'd ended up with negative 495. This one would have ended up, yeah, so this guy, this piece here, oh, I'm sorry. This piece inside the circle would have ended up being negative 495. And you take negative of that, you get the positive. They're opposite signs. That's the long and the short of that. Okay? Let's see, what else is there to talk about? Ooh, here's a fun one. This one always freaks people out. Suppose you've got some function here, whatever it is. Here's a, here's b, and you want to find this integral, right? That would be the true area, correct? Cool. And so we know that this area is equal to the integral from a to b of some f of x dx, right? But you're like, I don't know, Jay, if I would like to know like some upper and lower bounds for this. Sure, good for you. Suppose I said to you right across here, here's some value, let's just say that's y equals, I don't know, some value, let's call it big M. You with me? So what a person could do, if you will, is he could just take m times b minus a. Are you with me on this? And what would that give you? It would give you a, well, it would give you a box. And what do you know about that box compared to this region in here? Well, it's bigger, that's right. So it would be bigger than that. I'm going to say bigger than or equal to because in a minute I'm going to let things change a little bit, okay? And if you picked a value down here, let's say y equals some little m, that y then, little m, this is big M, dummy, little m times b minus a would be less than that, true? Well, that's what that's saying to us. So what oftentimes is given to you a little bit differently, and let me just show you this, it'll be written like this. Now, in essence, what you're going to get is what I had written a minute ago. Okay? Because think about this. What is this side? I'll do this. I'll do one of them, and the other one's the same. What if you integrated m with respect to x? Well, you'd get big mx from a to b, and that would be big M of b minus little m, or big M times little a. And so you could factor that out, and it would be exactly what I said it would be. And the same thing is true on this end. And the idea is it just gives you a way to pinch it between them. It's kind of, if you will, upper and lower bounds. The big kids call that the comparison theorem. And it's not very hard, of course. But what it does is it gives you an idea, a way of judging to see if that seems reasonable in any way, shape, or form. Okay? Here's a question for you. Suppose you had this equation here, f of x. Oh, well, I wrote g of x, so oh well. And you have this function here, f of x. Oh, that's cool. And here's some region, x equals a, x equals b. Are you with me on this? Now, tell me this. The integral of f of x on that interval and the integral of g of x on that interval, who is bigger? Well, since f is bigger than g on the interval, then this integral is also bigger on that interval. Now, you step outside of that interval, well, all things are off. All bets are off. All bets are off outside of that interval. Now, outside of that, you're going to have issues, of course. Going to have problems, things happen. All right, but if you have that true, it's not that big a deal. Okay? And I think there's just one more thing I want to mention from section 5.2 before you just really get into it and get it going, and that is if you have a function, I always use the same function, whatever. And here's x equals a, here's x equals b, here's x equals c. The integral from a to c of f of x dx is equal to the integral from a to b plus the integral from b to c. Okay, it has a name. It's called the integral on adjacent intervals, I think that they call it. It's not a big deal to me. I just care that you can get the job done. That's what matters to me. Now, in this section, the thing that kills people in this section, and it drives me bananas, because they want you to not use calculus so much as they want you to use geometry to find these areas, okay? And so they give you this equation here, for instance. This is the equation y equals 2x plus 4. And they want you to find the area under it between -2 and +3. And they want you to do it using geometry. Now, what do I mean by that? Well, what I mean is if you take a look at this, clearly at -2 it hits here at 0, correct? And at +3, you put 3 in there, you go up to 10, correct? Okay, this is 10, and then from 3 over to -2 is a distance of 5, right? Why, that's just a right triangle, so 50 times, that's 50 divided by 2 is 25. That's your answer. And you can use it, and you can do it via geometry. Here's another one that freaks people out. Here's the absolute value of x. And they want you to find y equal, they want you to find the integral of the absolute value of x from -2 to 3, apparently. Well, -2 is here. +3 is here. Okay. Well, these are two right triangles. Notice that they're both positive, however. So this is 2 by 2, so it's 4 divided by 2 is 2. This is 3, this is 3. 3 times 3 is 9, divided by 2 is 4.5. Add them together and you get 6.5. Okay. Another one that freaks some people out is this guy. Y equals the square root of 16 minus x squared. Well, Jay, isn't that half a circle with a radius of 4? That's correct. So if a person were to integrate this from 0 to 4, okay, there's my equation. But I'm only interested in it from here to here. You with me? From when x is 0 to x equals 4. So that means that's 1/4 of circle with radius of 4. So pi radius squared divided by 4. So that would be 4 pi. Whatever that is. 12 point something. Okay? So that's the thing that kind of annoys me in the first part of that section. I like it, but it, again, kind of annoys me a little bit. Okay. Another ones that come up in this one I think are kind of fun is they want you to do things like this. So, for instance, number 40 is one that kind of is handy. 9x minus 4x squared dx, and negative 3 to 3. They want you to use the properties of integrals. So first thing I notice is I can split them into two integrals. Not really sure why I want to do that, but I'm going to do it anyways, just for a good time. Okay, and then I realize, hey, look at that. Nose. I've got constants, so I can pull them out. Good for me. And then let's take the antiderivative. So that's going to be x squared over 2 from negative 3 to 3. 9 times that. Minus 4 times. It's going to be x cubed over 3 from negative 3 to 3. And so that's going to be 3 squared is 27 halves minus a minus 27 halves times 9. And that's going to be 27 thirds minus a minus 27 thirds. And so it's going to be 54 halves times 9 minus 54 thirds times 4, which is 18 times 4 is 72 on this end, I think. And then this one is 27 times 9 is, I don't know. That makes sense. 243 minus 72. 171. Ta-da! And that's it. That's all there is to that. Okay? Not very difficult. They just wanted you to see that. Here's one that might pop up to you and it might kind of weird you out, or you might think, geez, that's kind of an odd problem. It might be. Don't freak out about it. This one might come along. Don't panic. That's just x cubed over 3 from a to a squared. What does that even mean? Listen, I don't know, and I don't care. I'm just told that somebody wanted me to take an integral, and that's what I'm going to do. Mine is not to reason why. Mine is just, but was it the charge of the light brigade, right? There we go. Bam. That's it, baby. That's all I can do. Well, it's not all I can do. Let's see how many ways your book could mess this up. Why? First of all, I messed it up. First of all, your book could pull a 1/3 out. So they might write it like that. My guess is they don't. My guess is they pull an a cubed over 3 out and write it as a cubed minus 1 just to irritate you, to see if you're paying attention. By the way, when you ask me, is that why the book does it? The answer is probably yes. Okay? Because that's literally all there is to it. Okay? So you get some of that stuff there. It's pretty straightforward. It's, you know, like I say, it's almost kind of fun. When you get to some of these guys later on, I will ask you problems like this. Not so much in the online homework, but in the part of the homework where you're going to submit it to me. And we're going to see what happens in that regard. You'll see some of these perhaps. From 1 to 2 of f of x dx. Now, they will have told you that from 0 to 1, the integral is equal to 1. And from 0 to 2, the integral is 4. And from 1 to 4, that integral is equal to 7. Well, how in the devil are we going to find from 1 to 2? Well, somebody might rightly say, hey, look, there's my f of x, whatever. And I know that from 0 to 1, this region in here is 1. And I know that from 0 to 2, I know that this region now is 4. So then the question might be then, or the question is rather, what is in there? Okay. Well, most people go, oh, it's 3. And they're right. It is 3. But why is that? Because what we're going to do is we're going to take the integral from 0 to 2, and we're going to subtract the integral from 0 to 1, and we're going to be equals the integral from 1 to 2. Now, how do I know that works? Well, it is just that adjacency formula, if you think about it. If you were to add this to the other side, you would get that the integral from 0 to 2 is equal to the integral from 0 to 1 plus the integral from 1 to 2. And that's exactly the same formula. Okay? So for the most part, I think that you'll find it to be, I hope, pretty good. We'll see if that makes sense to you as you go along. Again, by all means, any questions, you just give me a shout out. I want to help.